Good. So well, this presentation it's now on SIMAP, the integration that we did in Teraflow of this service and infrastructure maps. This is a collaboration between the ETSI SDG, Teraflow SDN, and the ETSI ISG Fix 5G. So it's a very fruitful result in my humble opinion, and I hope it likes you. First of all, I will go a bit more in detail on these service and infrastructure maps because as I was mentioning, I think it's something very interesting and it's good to understand a bit. So what is SIMAP? I was mentioning that in previous presentations, but this is a data model that provides a unified view of a network operator of an operator's network and services spanning physical infrastructure up to the service and intent topology. Okay, so then it defines the topological entries of each layer. This includes the networks, the nodes, the links, termination points. It also supports relationships within and between layers. So we can, for instance, represent how a physical link, for instance, is supporting a set of service flows. And it also can be linked to other models and other data. So instead of replacing things and creating things from scratch, it can just complement and augment. So you can incorporate in the SIMAP things like inventory, observability, configuration, assurance, KPIs, whatever you need. Then, well, the some or why SIMAP matters and some key features. On one side, what I was mentioning, it provides unified multi-layer understanding of the network, showing from the service to the physical layers, through the packet layer, the optical layer, and so on. You can navigate up and down the different layers. You can also provide operational intelligence featuring impact analysis. So given that you have a view of the whole network, you know all the services, you know all the different resources that are involved here and there. Let me give it a pointer. Uh, you can investigate which will be the impact. So if, for instance, one link it fails, or you assume one link fails, you can extrapolate which upper layer services or virtual links or whatever will be impacted. So everything is collected in the model. It provides, as I was mentioning, inventory and topology data, so you can perform queries and find resources, dependencies, alternate paths, whatever. And interestingly, it enables to deploy tools like, for instance, network digital twins to perform simulations, what if scenario analysis, identify potential issues, or enhance the planning for future topologies, and so on. It's based on standards, so that means it's well, it's API driven, it's open, it's multi-vendor, which is very very interesting. And then you can provide multiple viewpoints from the point of view of intents, logical, physical, whatever. And it can be expanded, as said, because it relies on existing and coming data models. And well, this is more or less what I was mentioning. This can help a lot in things like mm, maintaining live, plan, and forecast map states, because you can simply implement different copies of the same network, but you flavor them maybe with past data, with instant data, with forecast data, whatever. So you can do whatever you want. And at the end, what I was mentioning, it's a very good enabler for digital twin and automation pipelines. In terms of the key benefits, I was already presenting this slide before, so I will go quickly. So it provides better network visibility, it provides improved network management, it enables increased automation, optimization of resource allocation, service reliability. It becomes an enabler for network digital twins. It provides flexibility and scalability, security and scalability again. It's redundant. And here are some of the relevant standards that are still in draft. And there is a very interesting point that maybe you find here a familiar name. So Oscar González from Telefónica. It's one of the TSC members of Teraflow SDN, and it's also one of the contributors of these drafts. So it's very good because then we can be very well aligned with the drafts. And for sure, we can provide feedback of whatever we identify and we realize about the utilization of these drafts. In terms of how it was architected inside Teraflow SDN, I was introducing the architecture some time ago today. Essentially, we incorporated a new component in Teraflow, which is named as SIMAP connector, and this component has the counterpart of the SIMAP server. Okay, ideally, these two components become what in the simplified architecture it's named as the SIMAP module. Why do we have these two separated elements? This SIMAP connector essentially it's the element that enables the Teraflow architecture to interface with SIMAP. And the other one, this SIMAP server, it's a RESTconf-based server implementing the SIMAP data models and featuring a database for storing the information. That way, having this separation, it enables us to implement or to deploy this SIMAP module in two ways. So we can have the two modules in the same Teraflow instance, or we can have a centralized SIMAP server and then one SIMAP connector per Teraflow instance so that the different Teraflows, for instance, working on different layers of the control and management plane, they can make their contributions to the SIMAP server, having an integrated view in a single SIMAP instance of the details from the different layers. Then, in terms of, well, this is more or less what I was mentioning. So how is this SIMAP server implemented? Essentially, it's based on the IETF RFC, the 8345, which is the data model for network topologies. This is the basis for SIMAP, as it is defined in the last version of the draft. And then on top of this network topology data model, you can implement augmentations, okay, and extend it with whatever you need. In this case, given that at the time of coding these features, there was still no draft available in terms of how to implement or how to map telemetry data on the different elements, we went for a custom telemetry set of endpoints, very basic, but just to kickstart things, that essentially consist in augmenting the representation of a link with SIMAP telemetry and providing which is the bandwidth utilization as a percentage, which is the latency of the link in milliseconds, and then which is the list of service identifiers that relate to this link. That means essentially the list of services that are contributing to this or are affecting, let's say, this bandwidth utilization in the link. Then, in terms of the node, well, we decided to incorporate here the CPU utilization of the specific device and also the list of services that are traversing this node. Well, I was explaining that this SIMAP then can be deployed as a local TFS module. So it's bound to a TFS instance. So you get an all-in-one deployment, or you can have the SIMAP server as an external module so that you can have multiple Teraflow instances that can contribute to the model that is represented by the SIMAP server. So then you can get, for instance, a hierarchical set of controllers or specialized controllers to provide their inputs into the aggregated view. In terms of the connector, essentially the connector, what it does is to listen for internal TerraFlow events. It collects these events, in particular, the ones that are implemented right now are events from changes in devices, changes in links, and changes in services. And then these events are translated into actions or updates that are injected into the SIMAP server. So that way, in the SIMAP server, you get an updated view of what the TerraFlow controller sees. The second feature that is implemented in this SIMAP connector is a set of synthetic telemetry data generators. The point is that here, for facilitating and for this initial experiment, we decided to go with synthetic data generators that you configure with some parameters and then generate telemetry data following a specific waveform that you can configure or generate it randomly. Then this information is collected by means of some telemetry data collectors. These collectors interrogate, let's say, the generated data and feed the telemetry data aggregators that take data from different collectors that correspond to different resources in SIMAP and perform an aggregation. I will give you I will show a picture later and maybe it will be better understood. And finally, we feature a gRPC client that enables to establish and terminate subscriptions from the NBI component of TerraFlow so that an external element can connect to TerraFlow and say, look, I want to open a telemetry stream to collect this specific set of information. And then all these elements here in the SIMAP connector interface with the external SIMAP so all these elements here interface with the external SIMAP server, retrieve the data, perform the appropriate aggregations, and through the NBI, it keep reporting the data. Okay. Well, this is the workflow. I will not go through all of the steps because it's a bit sophisticated. The only thing that I want to mention is that the interactions between the different controllers is made by means of young push. So what we have is that we create young push based subscriptions, and then we get asynchronous notifications with the data based on the subscription parameters. I elaborate a bit how it works. So expanded, the idea is that the upper layer system that wants to get telemetry data issues a post request for establishing a subscription, and it provides an XPath filter, okay, on the data store that says, for instance, for this specific slice, I want to get the information, okay, and I want this information maybe every 500 seconds or whatever value you want. This period is in seconds. Okay. Then what happens is that this thing, it's represented here. Well, it's not shown here, but it's symmetrical in all the places. Internally, the controller that is getting this request, it performs a find of data and correlation of resources through this SIMAP representation. So it says, okay, for instance, this specific link or this slice or whatever, it's supported by these specific physical links or underlying virtual links, whatever. It decides whatever it's needed. If needed, it issues appropriate subscriptions to underlying systems, so it can be hierarchical. All this it's supports hierarchy, and then opens the appropriate underlying streams, collects the data, and starts performing the aggregations so that the information that is retrieved is aggregated. After this request, whenever all these underlying subscriptions, preparations, and so on is done, the system retrieves. Here is a simplified view. We one arrow here and and another arrow here, but the idea is that after this post, we get a notification saying, okay, your telemetry subscription is available with this identifier, and you can connect to this URI to get your telemetry stream, and then we issue this get request to this URI that we have here, and it opens a stream that keeps reporting notifications with the data. And these notifications, well, depends on what you provide here in the filter. But if you point, for instance, to a specific filter that targets the telemetry of a specific element, you will get the materialization of this tree with the appropriate values for the specific resource that you subscribed. Okay. Then, in terms of the experimental assessment, well, we went for this scenario here. On top, we had Camara. Then we had an end-to-end service orchestrator that was based on OSM with some extensions for this setup. And the part that it's more focused on Teraflow SDN is that we had here a hierarchy of Teraflow controllers, one for the end-to-end network orchestrator, another for the fixed 5G aggregation network controller, and then another for the IP transport controller. Okay, so in this case, you can see this is aligned with the view of the ETSI ISG fixed 5G architecture. And you can see here that we are managing the IP layer with Teraflow, then the aggregation of the optical transport network and the IP. It's down here at the aggregation network controller, and then on top, the end-to-end network orchestrator integrates both the transport network with the access network. Okay, so at the end, we get an integrated view of the end-to-end segment besides the cloud, for sure. And what we were showcasing in the demonstration is that thanks to this information that we collect by means of this SIMAP infrastructure that we were, or framework that we were implementing, we can have, for instance, a gamer that initially connects to a specific, to the cloud to get access by means of the best effort network at the IP layer. But if at some point there is congestion, the connectivity is not good enough, whatever, it can switch to the premium services that use the deterministic optical transport network. For sure, it's more expensive, but well, that way the service is kept. If the user accepts to pay for these premium services, it can get better performance. This is the hierarchy, what I told you that what I promised before, how it relates the different elements in SIMAP. So imagine that we have at the bottom this physical network. We can say, okay, at the IP segment, the virtual link that connects the ingress and egress provider routers, it's represented by an aggregation of link L5 and L9, for instance, because in this case, the path follows the connection follows this path. So that means the latency will be the maximum between the two. The latency is the sum of the latency of the two links, but the utilization is the maximum of the two. So if this link has 75% utilization and this has 95, the end-to-end or this virtual link utilization is 95, is the maximum. And then we have this virtual link in SIMAP. To go to the aggregation network, okay, this virtual link is the aggregation of this physical link plus this virtual link plus this other physical link. So all these things is represented in SIMAP, and at the end-to-end segment, it is represented by this physical link and the virtual link that goes from here, from this point till this point. Okay, that is this virtual link. So that way you can have this hierarchical view of the elements, and all this information is stored in this SIMAP server. And well, the demo in a very quick sketch to prevent showing you the long video. Essentially, imagine that we have the service that is provisioned. Right now it's going through a specific path through the IP network. At some point, we detect that maybe the latency is suffering an increase, that it's violating the recommendations of the game developer, so the quality of experience of the user might be degraded. Then the user gets a notification saying, look, guy, do you want to promote to a premium service? If it says yes, okay, then you get promoted, and then your connection now goes through the premium services and probably going to a premium server, not the original best effort server. And well, at a glance, that will be the demonstration. What's next in terms of SIMAP? Well, we have many things to implement. We, for instance, can leverage network digital twins, as I was mentioning. We can implement what-if scenarios, retrieve more structured telemetry data with the state. We can implement things like solutions, enhance, let's say, the solution to be more aligned with the drafts, because these drafts keep going for sure, so we will have to align. But the good point is that we had initial validations. More future work we can do, well, improving the different features in the different components, because right now we are mainly relying on emulated telemetry data, probably migrate to the new monitoring analytics automation framework, because right now it's implemented in a more or less toy or example way. And then we have to implement, for instance, in the web UI, the user-friendly views of the SIMAP with all the elements, and well, and it can, as I was mentioning, explore the use of SIMAP as an external, as an enabler for the network digital twinning. And that will be it. I don't know if there are questions, comments, something you want to add.